Now, we just now said that only when the wavelet satisfies, that there is some similarity here between the integral in expression 5, the final integral here, and the one for the admissibility constant, and also that the admissibility existence of the admissibility constant is a requirement for the scaling function, and that is exactly what we are saying here. When the wavelet satisfies the admissibility function, the scaling function can be thought of as the impulse response of a low pass filter, pretty much like how we have been treating the wavelet as the impulse response of a band pass filter, or in other words an infinite set of band pass filters in the low frequency range is being replaced by a single low pass filter. Either of these interpretations is okay. Now, why is this true? That is, how can I think of phi of t as the impulse response of a low pass filter? Now, to see this, observe, that is the first point, that something that we have used earlier, that the approximation coefficient L is a convolution of x with phi of minus t. Well, whether it is phi of minus t or phi of t, it is almost the same. If one is a low pass filter, other is also pretty much acts as a low pass filter. What is happening here is convolution of x with phi of t, and we know from linear systems theory that convolutions are nothing but filtering operations. What kind of filter is phi? How do I know? Well, simply evaluate the phi of omega at omega equals 0, like the way we did for the wavelet. We said the wavelet is a band pass filter primarily because its magnitude, that is the Fourier transform of the wavelet, at omega equals 0 is 0, because wavelet is a 0 average function, and we know therefore that psi of omega at omega equals 0 is 0. Now, what do we want for a low pass filter? The Fourier transform of this low pass filter, or the frequency response function, is what we say, Fourier should be non-zero at 0 frequency. That is fairly obvious, because low pass filters have necessarily a non-zero magnitude in the FRFs. So, to see whether the phi of omega has a non-zero value as omega goes to 0, all we do is we evaluate the integral that we had in equation 5 here in the limit as omega goes to 0. If the magnitude is 0 non-zero, then phi of omega also will be non-zero. Therefore, it is sufficient to evaluate the limit of the magnitude or the squared magnitude, and what we have here is nothing but the admissibility constant itself. In other words, the value of the squared magnitude of the low pass filter at omega equals 0, or the FRF at omega equals 0, is nothing but the admissibility constant, and we want this to be bounded and non-zero, and that also tells us that only wavelets that are admissible will have scaling functions, right. And therefore, what we have here, that the scaling function exists if and only if the mother wave satisfies the admissibility condition. Consequently, the complex Morlet wave that we have does not possess a scaling function. Why? Because the admissibility constant for this particular wave does not exist. In other words, it is unbounded. The other way of saying it is, strictly this Morlet wave is not of 0 average. However, as when you choose omega naught in the range 5 to 6 roughly, then the average of this wavelet is of the order of 10 power minus 5, but we and of course, C psi is going to be bounded, but very large value, and we are not going to really consider that as something that satisfies the requirement here. Strictly, we want the admissibility constant to be finite for all possible values of the parameter. Now, as I mentioned earlier, the phase of the scaling function can be chosen arbitrarily. The only requirement is on the magnitude, squared magnitude, which depends on the admissibility constant. So, that is how the wavelets and scaling functions are tied together. As a simple example, let us look at the Mexican hat wave. Now, here there is some confusion in the literature For example, if you look up the documentation on wave fun routine that we have seen earlier in MATLAB's wavelet toolbox of release 2014B, the documentation would say there exists no scaling function for the Mexican hat wave. Unfortunately, that is not entirely true. It is true only when you are using the Mexican hat wave for multi-resolution analysis or DWT. But if you are using Mexican hat wave for CWT, the scaling function exists as given in this equation 7. In fact, this expression is given in Mallet's book. So, the Mexican hat is a second order derivative of the Gaussian e to the minus t square by 2 sigma square, and the C1 here is a constant that ensures unit energy for the wavelet. In other words, integral mod psi of t square dt should be 1. Therefore, we have this constant C1 and I have given the expression or the value for C1 here in equation 7. Now, this has an admissibility constant pi times C1 square sigma, and the scaling function can be derived starting with this equation 5 and letting the scaling phi of t or the phase to be not exist, in the sense we do not really consider the phase, we let phi of omega to be real valued, and that is exactly what we have here. The phi of omega is real valued. So, you from equation 5 you get an expression for mod phi of omega square, and you take the square root and you let phi of omega be real valued. So, you throw away the phase because that is free to choose. I have plotted the Mexican hat wave for you. The name obviously arises from the nature, that is a shape of the wave that you see here. It looks like a Mexican hat. For those of you who have not seen how Mexican hats look like, then I think you can go to the net and see how Mexican hats look like. It is just a fancy name for this wave. And what you see on the right is a scaling function. Observe that this Mexican hat wave on the average will have 0 value, because it exists both to the above 0 and to the bottom of the 0 line on the y axis, whereas the scaling function should not have a 0 average, because that is a requirement for a function to act as the impulse response of a low pass filter. And in fact, if you work out the area, it should actually work out the magnitude square of phi of omega at omega equals 0, you will get the C psi. And what I have shown you here is phi of omega, not phi of t. So, I am sorry about the earlier statement about the average not being not 0, but you can obtain phi of t by taking the inverse Fourier transform of phi of omega and plot it for yourself. So, one way is, if you can't do this analytically, evaluate phi of omega at different values of omega and then use the inverse Fourier transform algorithm in MATLAB or any other software and compute phi of t. You should be able to see the phi of t. So, it should be complex valued, because you have phi of omega to be real valued. And both these plots have been drawn assuming sigma to be 1. If you change sigma, things are not going to change much in the terms of shape, but what you will see is the widths being different from with different values of sigma. Now, we can extend or generalize this idea of scaling functions, as I said earlier, to an arbitrary reference point S naught. So, I am, instead of partitioning the scale axis at S equals 1 or partitioning the frequency axis with the reference point being the center frequency, I can choose an arbitrary reference point and I can say that now my reference point is S naught, and the scaling function produces at that scale S naught produces the approximations of x of t at scale S naught that complement all the details that are obtained by the wavelet transform at all scales less than S naught, right. Should always remember, lower scales you have details and higher scales you have approximations. Now, this idea, in fact equation 8 is the foundational equation for multi-resolution approximations that we shall learn in discrete wavelet transform, where we divide x of t or partition x of t or break up x of t into two parts, an approximation and a detail, and then we further break up the approximation into another approximation and detail, and that is how we proceed to a desired scale. So, in the end what you would have is an approximation or approximation set of coefficients of x of t at a very coarse scale, and then all the details starting from that coarse scale to the finer scales. That will become more obvious when we move into the DWT arena. As I mentioned at the beginning of this talk, the concept and the role of scaling function in DWT or multi-resolution analysis is pretty much similar to what we have learnt in CWT. It is only that the existence conditions are different. In multi-resolution analysis, there is an additional requirement for the scaling function, which is that its translates should constitute an orthonormal basis. Here there is no question of basis, anyway we have redundancies and so on. Therefore, the scaling functions and their translates in the case of continuous wavelet transform do not constitute any basis, they are highly dependent on each other. But whereas in DWT, remember we have been saying this, DWT is obtained by discretizing the scale and translation parameters. Therefore, there is a possibility for a certain choice of discretization that I can generate a basis. And for multi-resolution analysis, it is important that the scaling function constitute an orthogonal basis or orthonormal basis if you want normalizations. And that is why the scaling functions that exist for CWT may not exist for DWT, and that is exactly what wavefun probably tells you. So, you should not get carried away when wavefun says that Mexican hat wave does not have scaling function or any other textbook that says. You should verify if that statement is being made in the context of CWT or DWT. Otherwise, the scaling functions here, whether it is CWT or DWT, both take the role of low pass filters. In fact, when we move to DWT, we shall learn that the scaling functions are specified in terms of the low pass filter coefficients. Recall that one particular example where we tried to connect scale to frequency for a Dobeschi wave, and we said Dobeschi wavelets and the scaling functions do not have closed form expressions, rather they are specified by the low pass filter and the high pass filter coefficient. So, hopefully now that you are able to put that puzzle together a bit more better. Of course, when we discuss DWT, everything will be clear to you. There is yet another important distinction between the scaling functions used in DWT and CWT, which is that in CWT, as we have seen in this lecture, we have derived the scaling function starting with the wavelet function, whereas in DWT, specifically the multi-resolution analysis, we derive the wavelets from the scaling function. So, the starting point is a scaling function. We start with approximation spaces and then ask what basis functions exist for generating the complementary details. So, you want to keep this in mind when particularly we talk of MRA, you can compare notes. So, with these closing remarks, we will conclude this lecture. In the next lecture, we will get back to wavelets and discuss how to choose wavelets in CWT. When we talk of DWT, we will also talk about wavelets that are specifically used for DWT and how does one go about choosing there. The conditions are pretty much similar, and in the last lecture on this topic, we will look at a few CWT applications. Till then, see you, bye.